In this video, we're going to learn about electric power and how to do calculations with electric power. Power is the rate of transfer of energy, and sometimes you might see it in form of delta E over delta T. And change in energy is also considered work, so sometimes it's written as work per unit time. And what we need to remember is that a power is measured in the unit of watts, and a watt is defined as a joule per second. Electric power is the rate of transfer of electrical energy in a circuit. It's also measured in watts. So to make the connection between current, potential difference, and power, first I'm going to write out the formulas for current and potential difference. So current is defined as the charge per unit time, and potential difference is defined as the work done per unit charge. If we multiply these two values together, we get the charge per unit time. So we have IV, so we have charge per unit time multiplied by work per unit charge. We see that the charge will divide out, and we end up with work per unit time, which we know is power. So in other words, power is the multiplication of current and potential difference. There are two other forms of this formula, I squared R and V squared over R. And the way we can derive those is if we take Ohm's law, V equals IR, and we replace V and I respectively with these values, then we get these two equations. So, key thing to remember, power is always measured in watts, resistance is measured in ohms, current we measure in amperes, and volts we measure in volts. Let's do some example problems. A circuit contains a resistor with a resistance of 15 ohms connected to a power supply that provides a potential difference of 120 volts. Determine the electric power. So we are looking for the power. We have a potential difference of 120 volts, and we have a resistance of 15. And so we want to use one of these formulas. So we are going to use the P is equal to V squared over R. And so that means that the power is 120 squared over 15, which gives us a power of 960 watts. Next, we have a heating element with a resistance of 25 ohms, and it's connected to a 230 volt main supply. If the heating element operates for 2 hours, calculate the total energy consumed. So this is not a direct connection between energy and volts and resistance. However, we can calculate the power if we have the potential difference in the resistance, and then we can use this time to calculate the total energy. So first, we start off by finding the power. Power is what's going to connect these values all together. So the power is what we're looking for. We have a potential difference of 230. We have a resistance of 25. We have a time of 2 hours, which I want to put in seconds, so I'm going to convert that into seconds right now, which gives me 7,200 seconds. All right. So the power is going to be V squared over R, which is 230 squared divided by 25, which gives us a power of 2,116 watts. And power is defined as the change in energy per unit time. So the energy consumed by this heating element will be the power times the time, which is going to be 2,116 watts multiplied by 7,200 seconds, and that gives us an energy of 1.5 times 10 to the 7 joules. So that's the amount of energy consumed in 2 hours. So in example 3, we have an immersion heater used to heat 0.5 kilos of water from 20 to 80 degrees Celsius. The heater operates at a voltage of 240 and draws a current of 5 amps. The specific heat capacity of water is 4,200 joules per kilo per degree Celsius. Calculate the time required to heat the water to the desired temperature. So there's a lot going on here. Maybe let's start thinking about listing up some variables and see what we can come up with. Now, an immersion heater, that's the type of heater that's placed in a liquid, and the electrical energy is transferred into heat energy. So we have a mass of 0.5. We have a change in temperature, which I'm going to do now, which is 80 degrees minus 20 degrees, so that's 60 degrees. We have a specific heat capacity of 4,200 joules per kilo per degree Celsius. And then we have a potential difference of 240 volts and a current of 5 amps. And so what's connecting all of these things together? Well, we know that the MC and the delta T, we know that formula is Q equals MC delta T. That's the specific heat capacity formula, with Q being the energy. And IV, that reminds me of the power formula for electric power. So electric power is P equals IV. And so what connects these things here? How do we connect the energy with the power? Well, the energy is equal to the power times the time. And it turns out the time is what we're looking for here. So that's the connection between these formulas. Q is equal to power times the time. Q being the change in energy. So if we combine these two equations together, we get power times the time is equal to MC delta T. So the time is MC delta T over the power. But I know this is an electrical outlet, so the power is IV. So the time is going to be MC delta T times IV. If I want to calculate the time, I'm going to plug all these values in here. So I got 0.5, I got 4,200, I got 60, and we have 5 amps and 240 volts. And when I calculate all of this, I come up with a value of time as 105 seconds. And so that's how long it would take to raise the temperature from 20 to 80. Okay, in this question we have a motor and it's lifting 10 kilograms of mass vertically at a constant speed. The motor is powered by an electrical source with a power outlet of 120 watts. The mass is lifted to a height of 5 meters in 10 seconds. Calculate the efficiency of the motor. Okay, so there's a few clues in this question here. We have a 10 kilo mass being lifted 5 meters in 10 seconds. And so what we can do is we could figure out how much power it would take to lift a 10 kilo mass 5 meters high in 10 seconds. So our mass being 10 kilos, the height we travel is 5 meters, and the time is 10 seconds. And so one clue we have here is this is being lifted vertically up. So the only real type of energy is gravitational potential energy being given to this block or this mass. And so we can figure out the power because power is the work done per unit time. And in this case, the work done is the increase in the gravitational potential energy of this object. So the work done is going to be mg delta h all over time. And then our mass is going to be 10. We'll use 9.8 for g. The height is 5. And the time is 10 seconds. So we can figure out how much power it would take to lift all of this. And we get a power of 49 watts. So this is what came out of the machine. Now there's a little bit of a language thing here. The motor is powered by electrical source with a power output of 120 watts. Now that doesn't mean that the motor has 120 watts. It means the electrical source is putting out 120 watts. So actually we have to be very careful with our language here. But the power the input power is the 120 watts. That's what's going into the motor from the electrical source. And so this here that we calculated the 49 watts, this is our output power. This is what came from the machine. This is the useful work that we got done. Efficiency as a percentage is the power out divided by the power in times 100. And so our output power in this case is 49 watts. The amount of power going into the machine is 120, and we multiply by 100. So we get an efficiency for this motor of 40.8% efficiency.